So now your K is your, in the rate equation, is your rate constant. And this K is basically dependent on temperature. Normally what happens is that as temperature increases, then the value of K increases as well. Okay, so this is normally what's going on. I mean, is that clear that if the concentrations are constant and if you increase temperature, the rate increases, right? It increases because your constant, its value, its size increases. Is that clear?
Yeah, it's clear.
So moving on to this, I mean, this thing in the syllabus. Let me just copy this. It's AE minus A. Just 1 second. So we've got this relationship for calculating the value of K. Okay, where R and T, that's those are your, and I'll tell you how to calculate this. A is basically just a constant. I'll just copy this over here. A is a constant. It's just a constant TK for calculating K. Yeah, EA is your activation energy and T is the temperature in kelvins. That's it. TK, and R is your it's your old. We'll talk about how to calculate this entire thing. R is your gas constant, by the way, TK. So this one is called the. Let me get the spelling right. Just a second. 2 R's. And the other things, this is your temperature in kelvins. That's your gas constant, which is 8.31. And E over here is your activation energy. Now, what is done is that this thing, they take the natural log of this thing. Do you know what natural log is?
No.
You've studied log.
Sorry?
You know what log is? Log.
Yes, yeah.
Okay, so log, I mean, log basically expresses values in the powers of 10, right? So for example, if I have 1000, what's the log of 1000? Like what is 10 to the power of what is 1000?
Is it 2? I mean 3?
Okay, so it's going to be 3, right? So log basically expresses values in the powers of 10. What would be the log of this thing? And what's, I mean, how do you express
7?
this? 7, right? 3 and 4, yeah, 7. So it's 7. So log has. So why do you think we take log?
I'm not sure.
I mean, one thing is that it just converts big numbers into like really small numbers. So it's easier to plot graphs. I mean, log is like really important because like when you get very small numbers and very big numbers, like if I take the log of, let's say, 0.0001, I mean, in plotting all these three numbers is like really difficult on a graph. But I mean, what is log of this thing? What is this 10 power? That's 1, 2, 3, 4, 5. 10 power minus 5, right? So you get the idea that taking log of a value, that's it just makes it very easy to actually plot graphs. Is that clear?
Yeah, that's clear.
So then there's another property of log, which is that what it can do is uh, I've got these numbers, right? They're getting, let's say they're getting multiplied, right? So, for example, I'm multiplying 1,000 with this other number, which is the 10 power 7 one, right? So that's 1, 2, 3, 4, 5, 6, 7, right? So I'm multiplying the two numbers, right? So I'm going to get an even bigger number. TK, that's going to be now in terms of log. I mean, this is 10 power 3 and this is 10 to the power 7, right? So what will happen? What's your answer going to be? It's going to be 10 power 10, right? Is that clear?
Yep.
And in terms of log, if I take the log of this thing, then this will be 3 and this will be 7. So your answer, if I take the log of the product as well, that's going to be 10, right? So it's basically just simple addition, right? So what happens is that things that have powers, they just turn into simple addition, right? So so what that's going to help you with is that it's going to it's good. I mean, it's easier to actually make graphs because your exponential term gets wiped out. Okay, so I mean, it's 10 power 3, right? This 10 power 3 can be written as 3, like if I take the log of this, log of 10 power 3, it could be written as 3 log 10. Log 10 is 1 because it's 10 power 1. I mean, what's the log of 10 in powers of 10? That's 1, right? So that will basically give you 3. So the point is, the another thing that log helps you with is that exponential terms, they can simply be turned into linear terms. So it's easier to actually make graphs which are just straight lines when you take log. I mean, this thing is not a straight line. I mean, this thing over here, that right now it's not a straight line. You can't construct a straight line using this expression, right? Because it's got an exponential term, right? Like something that's x squared, right? That will never come out as a straight line. X cubed, that's not going to come out as a straight line, right? But when you take log of something, uh, the powers, they just go away. Like if I take log on both sides, this is log y. The other side would be 2 log x. Now it's a straight line. Because if I plot log of y versus log of x, I'm going to get a straight line. Is that idea clear as well? That log helps to convert expressions into straight lines. Is that clear?
Yep, that's clear.
Yeah, so now straight lines, it's very easy. I mean, on a piece of graph paper, it's very easy to actually. So two things. Log is good with it's easier to actually plot graphs. I mean, this is very useful. In scientific terms, you normally don't deal with numbers. You deal with logarithmic numbers. All your scales are like kind of log scales because you're gonna get small numbers. The smaller the value, you get -5. The bigger the number, you just get 7. So it's much easier to handle these numbers rather than and talk about. I mean, rather than communicating this huge number. That's why everyone deals with log. Plus, exponential terms, they just turn into addition, subtraction, and uh, any exponential term, it just becomes a linear equation. So you get straight lines. So that is exactly what's going to happen over here as well. Do you know what the difference between log and natural log is?
So one is log 10 and the other is log e.
Okay, so the base is different, right? Log
Yeah.
normal log is base 10. That means it's 10 to the power something. Natural log is e to the power of something, right? E is 2.7 something. So we're gonna take the natural log, which is so that's ln. So that's Take the natural log. So it's going to give you ln k. On the other side, it's going to give you ln a e minus ea over rt, right? So this ln k remains as it is, and the other one, if two things are getting multiplied, they become they just get added in. They turn into addition. Multiplication turns into addition in log. So that's ln a plus it's the power becomes, I mean, it's basically, this is going to be the sum. It's going to be ln a plus ln e, this whole thing, right? So let me do it in two steps. Minus ea over rt. And then it's going to be ln k. This will become, the power becomes the coefficient. So it's going to be minus ea over rt. ln e. Now ln e is 1. Like you get e to the power of 1 is basically e, right? So you could take the natural log of e, like you take the log of 10, that's going to be 1. So natural log of e is going to be, it's just going to be 1. Okay, is this clear? You end up with this expression. Is that clear?
Yep, it's clear.
Now, when you end up with this expression, your constant, what you can do, I mean, this is a constant. So that's, you can compare it with y is equal to mx plus c. Let me just rewrite this. This is ln k. I'm going to write this as minus ea over r 1 over t plus ln a, right? Now what we can simply do is, this equation looks like y is equal to mx plus c. So your constant, your Arrhenius constant was basically this thing. X is 1 over t. Your gradient of the graph is basically this thing, E over R. So you can find that out. So all you have to do is basically you just have to plot. You have to plot K versus temperature or 1 over temperature. And you will be able to figure out all the constants to figure out K. So you'll be able to figure out. So you have to, what you have to do is plot ln k versus 1 over t. And your gradient would be equal to minus EA over R. Now, you don't really get questions on this. It's just an experimental thing that that you have this relationship of K. I mean, you know how to calculate K, right? I mean, we did this last time. Yesterday we learned how to calculate K, right? So you can calculate K, right? K has this relationship with respect to temperature and the activation energy and the gas constant. And K varies with temperature, right? So all you have to do is if you want to calculate the constants over here, so all you have to do is you have this equation in front of you and you can, let me highlight this equation. Just a second. So you'll be asked experimental questions where data would be given and you just be asked to figure out E over R. Is that clear?
Yep, that's clear.
Because that's one thing. And where's the Okay, so this is just experimental data. You just have to plot that. Okay, so it'll just give you data, and you'll just figure out that. The other thing is, we did talk about this, that if temperature increases, the rate constant K increases. The other thing is, so then there's I'll talk about one more thing about this. How do you calculate experimentally? Let's say we're gonna try and calculate. I mean, although what we did was experimental, so calculate experimentally the order of reaction, or not the order of a reaction, but order of a specific reactant. And let me also add that, just one second, right at the beginning, just a second. Initially, we did talk about orders, right? Okay, so I told you that order of reactants. Here, let me add a point over here. I told you that X and Y were the order of the reactant, specific reactant. That how does it depend on A? How does it depend on B? Right? If they talk about the order of a reaction, that's the sum of the two orders. So in this case, it's going to be X plus Y. So if one of them is order 2, the other one is order 1, so the total order of reaction is 3. Is that clear as well?
Yeah, that's
Okay, moving on. यहाँ पे. So I'm going to talk about finding a method to figure out the experimental. Like if you're in the lab, then what you're going to do. So I've got this reaction, which is Mg. Let's do another reaction. Let's say let's let's just pick the halogenoalkane reaction, right? So OH ions are added. There's going to be another C. And your CLNs get knocked out, right? So let's say you're given this reaction and you have to figure out experimentally, you have to design an experiment where you have to find the order of reaction. Like it's simple, and you have to find the order of reaction with respect to OH ion. So how are we going to perform this experiment? Now, the first thing is, what is rate? Rate is, I mean, you have to think about it, that you have to measure rate, right? How does rate change? So what was rate? Rate was any change with respect to time. So now in this experiment, what change can you actually measure or time with a stopwatch? What's the possible change that we can actually measure over here?
is it maybe how many Cl minus ions are produced? So like the concentration?
And how would you measure that? Like, let's say the experiment, like the reaction is going on. So how would you measure the amount of CL lines?
I don't know.
Any other thing that you,
Like a change in mass over time, maybe.
whose mass is changing? I mean, there's no gas being produced, so the mass of the solution remains constant, right? Everything is still part of the solution. I mean, we need to figure out a change that's happening during the reaction that we can measure. I mean, there are a couple of things. For example, I mean, this is something that you have to think, right? I mean, you have to figure out like how would you actually measure the speed. So, for example, what you can do is you've got OH ions, right? So that means the pH is changing, right? What is OH? OH is an alkali, right? So maybe there's a change in pH, right? The OH ion will get used up during the reaction. If it gets used up, that means the pH will become, it was alkaline, now it's not, it's no longer going to be alkaline. So you can time that. Like what amount of time is required for the pH to go to 7? Is that clear? Or is this clear?
Yeah, that's clear.
Which of the reactants has to be added in excess? Like you're trying to find the order of this reactant, right? So which of the reactant needs to be added in excess? Because you have to keep the concentration of all the other reactants constant, right? So what you're going to do is you're going to try and keep this reactant in excess. You want it to have constant concentration throughout the reaction so that it does not interfere with the speed of the reaction. Is that clear? Was that clear?
Yep, that's clear.
So you want that one to be having constant concentration. You want OH ions to change, right? We figured out a way. I said that's one thing. The amount of time. Is there another possibility? Another possibility could be that what you can do is you got Cl ions being produced, right? And you know that Cl ions they produce a precipitate. When do they produce a precipitate? When you add silver ions. With So you can add silver ions to the solution. So what you can do is you can time uh, using a stopwatch for, let's say, half a centimeter of precipitate to be formed. Let's say you're doing it in a test tube, and in the test tube, as soon as half a centimeter of precipitate is formed, you stop the stopwatch. If the reaction is quick, that happens very quickly. If it's slow, then it takes a longer time. Okay, is this clear?
So you know how you wrote that we need to measure the amount of time for the pH to be 7?
Yeah.
So what does that actually show? So it just shows that the OH minus is being used up because it's getting less
So
alkaline.
it's going to become less alkaline, right? I mean, initially it's going to be alkaline because you're going to have OH ions, and then it's going to get used up, right? So that would mean that the reaction has stopped. So if the reaction happens quickly, then it's going to take lesser time for the pH to go to 7. If it's happening very slowly, then it's going to take a very long time. So the point is that in this way, you can figure out how quickly you can measure the speed of the reaction. You can measure the change that's happening with respect to time. Is that clear?
Yeah, that's clear.
So experimentally, you can just figure out so different reactions. Some reactions it's easy. Like if you have H2 gas getting formed, then it's easy. So what you're going to do is in this reaction, the only thing you're going to do is you're going to try and change the concentration of OH ions, right? So just a second. Hold on a second. It's my pen has stopped working. As I coming back to this, it's as I so I need to change. What I'm going to do is, if I want to figure out order with respect to OH and change OH and concentration, and find out what happens to the rate of the reaction accordingly. This is what we plan to do. Now, the problem with this approach is that how do you change the concentration of OH ions? Keep all the other reactants in excess. This is known as serial dilution. What you're going to do is that you're going to take OH ion constant. I mean, you'll have a certain solution. Let's say you've got OH ions and they have a concentration of 1 mole per dm cube. Now, in the first experiment, you're going to add, let's say you're adding 50 cm cube of OH ions in the reaction. At the same time, you're going to add some water to dilute it. In the first experiment, you're not going to dilute it. In the second one, you'll add 40 cm cube and then you'll mix 10 cm cube of water into it. In the third experiment, you're going to dilute it further. You're going to add 30 cm cube and you're going to add 20 cm cube water. And then you're going to add 30 cm and so on. Take your last one, it's going to be 40 cm cube and you're going to add 10 cm cube of water, right? So one thing that you're going to ensure is that you're going to try and keep the total volume constant. Like when you're diluting, you're going to take, I mean, you'll just be given one sample of OH. So you're going to do different experiments by changing the concentration of OH by just simply adding water to it. But you have to keep total volume constant. That's very important because if you keep the total volume constant, then the other reactants, their concentration is not affected. They don't get, because if you remember, concentration is moles over volume. You don't want the volume to change for the other reactants because then their concentration gets affected. So you have to keep the total volume constant so that
For the last one, wouldn't water be 40 centimeters cubed?
for which one?
For the last one,
मैंने उल्टा कर
14.
दिया. I mean, this one should be 10 and this one is going to be 40.
Okay.
As I keep total volume constant so that other reactant concentrations are not affected. Is that point clear, that why we want to keep the volume constant, right?
No, I don't understand. Like, what are you keeping the volume constant of?
For the other, I mean, see, for example, there are two reactants, right? So what I'm doing is I've got the first reactant, right? They're like 5 particles, right? And then I add, how do I show this? Then I add the other reactant. This is reactant A, and then I add reactant B, right? Now, when I add B, let's say in the first one, I'm adding 10 cm cube B. I'm going to add 40 cm cube of water to it, right? In the second experiment, I'm going to add 20 cm cube and I'm going to add 30 cm cube. No matter how much B is added, I want the same total volume of B. I mean, B is getting diluted, or you're changing the concentration by adding water to it, right? But you want the volume to be constant, right? Because that volume is going to add up with this volume. So if the volume changes the concentration of A, we want this concentration to be constant, right? And concentration is moles over volume. So every time I want the total volume of the solution to be constant, because I don't want to change the concentration of A. If A has 5 particles, I want every time those 5 particles should be present in the same volume. So its concentration never changes. That can only happen that when I add B, even when I'm diluting it, I just ensure that the volume remains constant, so that this does not get affected. Do you understand that point?
Yeah, I understand now.
Okay, so I mean, because you're adding less of B and more of water, B's concentration changes, but that does not affect A's concentration because its volume remains exactly the same. And always remember that when you mix two solutions, you're bound to change the concentration of the other one because the volume will change. But it should be, at the end of the day, it should always come out to be exactly the same so that it remains perfectly constant. Now, so that's one thing, TK. So that's how you're going to dilute it. But you have to keep the total volume constant. Last thing is you just figure out rate. Rate is what? Rate is 1 over time, right? It's inversely proportional to time. So you're going to calculate the rate. The reaction concentration is decreasing, so it's going to slow down, and it's going to take a longer time. So rate is 1 over time. Is that clear?
Yep, that's clear.
So now what you're going to do with this is you wanted to figure out the order with respect to OH and concentration, right? You wanted to figure out what A is. Now rate over here is you calculated rate to be 1 over T, right? Rate is 1 over T or 1 over time. And that's proportional to OHN concentration. Now OHN concentration is directly proportional to the volume that you're using. Like if you're using 50 cm cube, the OHN concentration will be 1 mole per dm cube. If you use 40 cm cube and you add 10 cm cube water, the concentration drops to, I mean, you can do the math, the concentration drops to 0.8 mole per dm cube. If you use 30 cm cube and you add 20 cm cube water, the 1 mole per dm cube concentration gets diluted and it becomes 0.6 mole per dm cube. Do you get the point that the concentration is decreasing proportionally as you keep on adding water to it? Is that clear?
Yep, it's clear.
So instead of OH ion concentration, I can use the volume of OH used, or the OH solution, right? Power A. Now, so now what I'm going to do is I'm going to take log. So this side will be log 1 over T, 1 over time. And that side would be A, the power becomes the coefficient. It's going to be log of volume of OHN. Now this equation exactly looks like y is equal to mx. Since we don't have a constant because I'm using proportionality. So what we're going to do is we're going to plot a graph of log of 1 over t, which is y versus log of volume of OH concentration, and your gradient happens to be the order. So plot log 1 over t versus log of volume of OH ions, and the gradient happens to be the order. Okay, so is this part clear?
Yep, it's clear.
Okay, so I'm just going to quickly summarize this. That first thing was I wanted to investigate the order with respect to OH and I wanted to keep this constant, so I added that one in excess. Okay, so figure out what would be in excess. Like if this is 0.01 mole per dm cube, then keep this as let's say 1 mole per dm cube. So that would be like 100 times in excess. So its concentration practically remains constant. How do you figure out, you try to measure any change with respect to time? So in this case, maybe the amount of precipitate produced with silver ions, time taken for that precipitate to form. You change the concentration of OH ions serially by adding water, proportional amount of water added. Always ensure the total volume is kept constant. The OH ion will get diluted every time proportionally. And just figure out what the rate is. It's going to take a longer and longer time for the reaction to finish. Then you just plot a graph of rate was 1 over time. OH ion concentration is proportional to the volume of OH ions. And when you plot it, you take log on both sides. A becomes the coefficient in the linear equation y0 mx, and that's it. Okay. So that's about it. Okay. There's an Idean clock which we'll do tomorrow, which we'll do in the next class. Okay. Tomorrow probably. ठीक है वर्दा.
Okay, and tomorrow will the class be at 6:30 or 6 o'clock?
Let's keep it at 6:30. ठीक है.
Okay.
Okay, take care.
Okay, thank you. Allah Hafiz.